Hey, welcome back. In this video, we're going to continue discussing the proof of the Stanley-Wilf conjecture. Last time, we talked about how proving the Stanley-Wilf conjecture boils down to proving that every permutation matrix has a linear extremal function. So we're going to prove that in this video. Before we get to the proof, we're going to review a few definitions and then we'll get into the math. So first definition, recall that the extremal function ex of n comma p is the maximum number of ones in an n by n 0-1 matrix that avoids p. And like I said in this video, we're going to prove that the extremal function of every permutation matrix is linear in n. And like we talked about in the last video, proving this implies the Stanley-Wilf conjecture. And the Stanley-Wilf conjecture again, it says that for every permutation pi, there exists a constant c such that this function u sub n of pi is less than c to the n for all n. And let me quickly recall what this function is. The function u sub n of pi is the number of permutations of 1 up to n that avoid pi. So we're trying to count permutations that do not have any subsequence with the same relative order as pi. And the idea of the Marcus and Tardos theorem is going to be kind of similar to what we saw with the proof from Klazar in the last video. So Klazar's proof, where he showed that the Ferretti-Hodgenall conjecture implies the Stanley-Wilf conjecture. He used a decrease and conquer technique where he took a 0-1 matrix and he partitioned it into a bunch of smaller 0-1 matrices. And he compared the extremal function of the larger matrix to an extremal function for smaller matrices. So in this proof, we're going to use a similar idea, but when we partition the larger matrix into submatrices, the submatrices will be a little bigger than the ones we used in the last proof. In the last proof, the submatrices we used were 2x2 submatrices. Here, the dimensions of the submatrices are going to depend on whatever permutation matrix we're trying to avoid. So to start the proof, suppose that P is a k by k permutation matrix for some k. And we'll let A be an n by n 0-1 matrix that has the maximum possible number of ones, ex of np, for which the matrix avoids p. So this 0-1 matrix, it has to avoid p, it has to have dimensions n by n, and it has the maximum possible number of ones, ex of np. And here's an important assumption. Suppose that n is divisible by k squared. So the inequalities we get in this proof will have a lot of n over k squareds in them, and these work out because n is divisible by k squared. And the construction in our proof is going to work out again because n is divisible by k squared. This will be fine, and the end of the proof we'll still get a bound that holds for all n, but we'll have to do something extra in order to get it from multiples of k squared to all n. So first thing we're going to do, which is kind of similar to the idea in the Klazar proof, is we'll partition A into n over k squared squared contiguous submatrices of dimensions k squared by k squared. We'll call these blocks. So I'm going to draw an example again. We're going to take k equals 2, and I'll take an A right here, matrix A. Okay, so there's our matrix A. And we'll say here that, actually, let me make a little larger. Gotta make it larger than that. Okay, so that's a good A, because that one's actually divisible by 2 squared. That's an 8 by 8. Now we're going to map A to a new matrix, B. And in order to find this map, we will partition A into contiguous submatrices of dimensions k squared by k squared called blocks. Here, k squared by k squared is 4 by 4. So our blocks, they're contiguous. So all of their columns are adjacent, all their rows are adjacent. And here's our partition for this matrix A. We define a new matrix B, and we take every block of zeros and we replace it with all zeros. And we take every block of not all zeros and replace it with a 1. So in this example here, we get 1, 1, 1, 1. So there's one example. Now let's consider a different example. Let's say this bottom right corner, I make that 0, 0, 0, 0. Now that bottom right corner, I have all zeros down there. So this entry is a 0. So this would be an example of the map which I define in this next bullet. So B is the n over k squared by n over k squared 0 1 matrix. So in this case, k equals 2, n was 8. So n over k squared is 2. So B is 2 by 2. It's a 0 1 matrix obtained from A by replacing each of those blocks that we got with a 0 if it's an all 0 block and a 1 otherwise. And like we saw in the last video, B must avoid P if A avoids P. So A was a matrix that avoids P, and I claim that B avoids P. And I leave that as a problem to you. So I pretty much explained in the last video why it's true, but try to think about it and process what I said in the last video and explain it clearly why B avoids P. And we can say that since B avoids P, and B is an n over k squared by n over k squared 0 1 matrix, by definition of the extremal function, we can say that B has at most ex of n over k squared comma p ones. And what does that mean about A? Well, we know that each entry of B corresponds to a block of A. So each 0 entry of B corresponds to a block of all zeros in A. Each 1 entry of B corresponds to a block of not all zeros in A. So we can say that if B has at most ex of n over k squared comma p ones, then A has at most ex of n over k squared comma p blocks with ones. In other words, blocks that are not all zeros. And we're going to use that later. So that's going to be a real important fact that'll come back. But I'll clear all the drawings for now. So now we're going to look at different kinds of blocks. And here is where the pigeonhole principle is going to come into the proof. So we're going to define 2 kinds of blocks called tall blocks and wide blocks. And these blocks are k squared by k squared. We already said that, but recall that's their dimensions. And we're going to give them these labels tall and wide based on the ones in the blocks. So we'll say that if the block has at least k rows with ones, we call it tall. And if the block has at least k columns with ones, we call it wide. And for each I from 1 up to n over k squared, we define the block row Ri to be the ith row of the blocks in A. Similarly, we define block columns. Cj is the jth column of the blocks in A. And it'll be useful to look at an example for these. So I'm going to draw another 8 by 8 matrix A. We'll take k equals 2, n equals 8, and A right here. Okay, so there's our matrix A. And we can define these block rows and block columns. So block rows, I will draw the labels to the right for those. So a block row R1, block row R2. In the block columns, we have block column C1, block column C2. Now let's see which blocks are wide, which ones are tall. So this block right here, the top right, let's look at that. So that block has at least k rows with ones, because k equals 2, there's at least 2 rows with ones. So it's both tall, and it has at least k columns with ones, because there's 2 columns with ones. So it's also wide. Now, this one down here, not tall, not wide, obviously, because it has no ones. And we can see that all of the blocks besides that bottom one are both tall and wide. So this one too is also tall and wide. Now, let's see an example of a block that would not be tall, would not be wide. So I'm going to draw a block over here. So this is going to be a block, k equals 2 block. Okay, so we'll consider 3 examples here just to illustrate the idea. So this block up top, it is tall because it has at least 2 rows with ones, and k equals 2 here. So at least k rows with ones. So tall, but it's not wide because there's only 1 column with ones. On the other hand, the one below it, it's going to be wide because there's 2 columns with ones, but not tall because there's only 1 row with ones. And then the one below that, this is going to be both wide and tall. There's 2 rows with ones, and there's 2 columns with ones. So hopefully that illustrates these ideas. And here is a problem for you to think about. So problem, prove that the number of wide blocks in any block column Cj is less than k times k squared choose k. Now for this problem, I want to give you a hint for this. Use the pigeonhole principle. Use the pigeonhole principle. And specifically, use the pigeonhole principle to show that if you had at least this many wide blocks in some column Cj, use the pigeonhole principle to show that many wide blocks forces a copy of P. So the permutation matrix we're trying to avoid, this permutation matrix with k columns and k rows, prove that the number of wide blocks must be less than this quantity, because if it was at least this quantity, then we could force a copy of P on those wide blocks. So greater than or equal to k times k squared choose k wide blocks. And this is specifically in Cj for a fixed j. So just for a single Cj, if we have at least that many wide blocks in that Cj, then that forces a copy of P on those wide blocks by the pigeonhole principle. So see if you can see, why does the pigeonhole principle even factor into this? Where's that k squared choose k coming from? So k squared choose k, I mean, we can think about k squared, that's going to be the, k squared is going to be the number of rows in the block. So k squared is the number of rows in the block. And then this k down here, we can think of that k, well, in a tall block or a wide block. So, I mean, wide block or tall block. So k squared is the number of rows and it's the number of columns. So number of columns or rows in the block, because it's a k squared by k squared block. The k down there, we can think of that as a lower bound on the number of columns with ones in a wide block, that k. We can think of it as a lower bound on the number of rows with ones in a tall block. So the k squared choose k. The k squared is coming from the number of rows or the number of columns in the block, and the k in the bottom is coming from the number of rows with ones or the number of columns with ones. And we're going to have a statement like this, the number of wide blocks. We're also going to have a statement like this for tall blocks. And I'm going to put that one up now. So you can use nearly the same proof to show that the number of tall blocks in any block row, Ri, is less than k times k squared choose k. So the same bound that we have up here, you can get that for tall blocks in each row. And you can use the pigeonhole principle for that as well. So again, this k squared choose k here, the k squared, this is the number of rows or columns in any of these blocks. And the k right here, these are corresponding to the k rows with ones or the k columns with ones. So that's a hint for how the proof of this problem works. And you don't have to prove both of these bullets, because the second bullet right here, this bullet, is almost the exact same proof as the bullet above it. So if you prove the one above it, it should be pretty obvious how the one after it works. Now, let's see why this implies what we want to get. So the total number of block rows is n over k squared, because our matrix A was n by n, and we partitioned it into k squared by k squared blocks. The number of block columns is also n over k squared. And we said that each block row has at most k times k squared choose k tall blocks. So that was each block row. And each block column, the Cj, has less than k times k squared choose k wide blocks. So we can use this to bound the number of ones in tall blocks and the number of ones in wide blocks in the whole matrix. And in order to do that, we can just multiply the number of block rows times the number of tall blocks that we got per block row and the number of block columns times the number of wide blocks that we got per block column. So the number of block rows, n over k squared, times the number of tall blocks per block row, we get n over k squared times k squared choose k. And that's using this bullet right here. And the number of wide blocks in A total, it's going to be the number of block columns, n over k squared, times k squared choose k. And that's from this bullet. We said the number of wide blocks in any block column is less than k times k squared choose k. So that's how we got both of those quantities in this last bullet down here. And so we can add them together and we can multiply by k to the fourth, because in any block in the whole matrix, the maximum number of ones we can have in that block is k squared times k squared, because the number of entries in the block is k squared times k squared. So the maximum number of ones we could have is k to the fourth. So the maximum possible number of ones in blocks in A that are wide or tall is going to be at most the quantity that we got in this bullet times k to the fourth. So we add these two together, we get 2n over k squared times k squared choose k. Then we multiply them by k to the fourth, and that gives us this quantity right here. And we can simplify that to 2 times k cubed times k squared choose k times n. Now, one thing to notice here, all this stuff is just a constant in terms of k. So the permutation matrix we're considering P, we're treating it as a constant. It's a k by k permutation matrix. So k is a constant here. So we just have a constant here times n. So this is good. This is going to allow us to get an eventual linear bound on EXNP, a bound of some constant times n, an upper bound. And the reason why we're going to be able to get a linear upper bound is because here we got a linear upper bound on the number of ones in tall blocks and the number of ones in wide blocks. So now that we bounded the number of ones in A that are in tall blocks or in wide blocks, we still have to bound the number of ones in A that are not in any tall blocks and they're not in any wide blocks. And we'll do that on the next slide. So blocks that are not wide and not tall. So we can see that if a block is not wide and not tall, if it's not wide, then it has fewer than k columns with ones. And if it's not tall, then it has fewer than k rows with ones. If it has fewer than k rows with ones and fewer than k columns with ones, then clearly it has at most k minus 1 squared ones. And that means that in these non-wide, non-tall blocks, the maximum possible number of ones is going to be the number of non-empty blocks. So non-empty block, the number of blocks that have at least a single one, times k minus 1 squared right here. So if we want to count the number of ones in blocks that are non-wide and non-tall, we can just take the total number of blocks that have any ones. And we saw on an earlier slide in this video that the total number of blocks with any ones is at most ex of n over k squared comma p, because the total number of blocks with any ones in A is the same as the number of ones in the matrix B that we obtained from A. And we said that B, it was an n over k squared by n over k squared matrix. So B has at most that many ones, ex of n over k squared comma p ones, and B was the matrix we obtained from A by changing each block into an entry. So each one of B corresponded to a block of A that had at least a single one. Each zero of B corresponded to an all zero block of A. So we can say then that the number of ones in A that are in non-wide, non-tall blocks, each of those non-wide, non-tall blocks contribute at most this many ones, k minus 1 squared ones. And the number of those non-wide, non-tall blocks is at most the total number of blocks with, so the number of non-wide, non-tall blocks with ones is going to be at most the ex of n over k squared comma p, because it's going to be at most the total number of blocks with ones. So number of non-wide, non-tall blocks with ones is less than or equal to total blocks with ones. So that's the key idea here. So we're basically taking a really rough bound there. So in order to get an upper bound on the ones that are in non-wide and non-tall blocks, we can just take that k minus 1 squared for the blocks being non-wide, non-tall, and then for the number of blocks that we use times that. Instead of taking the number of non-wide, non-tall blocks, we can just take the number of total blocks with any ones. And an upper bound we have on that is just the number of ones in B, which is ex of n over k squared comma p. So that's why we can say that there are most k minus 1 squared times this extremal function of ex of n over k squared comma p ones that are in non-wide and non-tall blocks. So now we have a bound on the number of ones that are in tall blocks, the number of ones that are in wide blocks, and the number of ones that are in non-wide and non-tall blocks. And we can just add them all together now. So when we add these together, it gives the total number of ones in A, and we get this upper bound, and it has the term that we just got, the k minus 1 squared times ex of n over k squared comma p. Then it has the term from the last slide. So this was non-wide, non-tall ones. And this right here is from tall or wide. And I'm going to bring this down just to mention this one more time, because the way I wrote that might be a little unclear. So this, what I'm writing right here, the non-wide, non-tall blocks. So the reason why we got that bound up there is the number of non-wide, non-tall blocks. And this should say with ones. So number of non-wide, non-tall blocks with any ones is going to be less than or equal to the number of total blocks with any ones. So this is a really obvious statement. So if we take the total number of blocks with ones and we restrict it to some subset, the non-wide, non-tall blocks with ones, we're going to have at most as many entries as we had in the original set. So a subset had size at most the original set. So it's a really obvious statement there. The number of non-wide, non-tall blocks with ones is just less than or equal to the number of total blocks with ones. And that's why we can say then that the number of non-wide, non-tall blocks with ones is less than or equal to ex of n over k squared comma p, because that's an upper bound on the number of total blocks with any ones. Because again, the number of total blocks in A with any ones is equal to the number of ones in B. And we said B has at most ex of n over k squared comma p ones, because B avoids p and B had dimensions n over k squared by n over k squared. So we got the number of non-wide, non-tall blocks with ones is at most ex of n over k squared comma p. And we said that in any of these non-wide, non-tall blocks, the number of ones is at most k minus 1 squared. So the number of ones in these non-wide, non-tall blocks is at most this quantity times this quantity, and that's how we got that. So hopefully that was a little clearer than I said before. Okay, so there's a little more to say. So we have the number of ones in A here. And now recall what we assumed about A. We assumed A was an n by n matrix. It avoided P. It had the maximum possible number of ones. In other words, the number of ones in A was equal to ex of np. So we have ex of np is less than or equal to k minus 1 squared times ex of n over k squared comma p plus 2k cubed times k squared choose k times n for every n divisible by k squared. So remember, we were assuming that. So the fact that we have these n over k squareds is fine because n is divisible by k squared. So now there's a little bit of the proof left. Before we get to the last part, I just want to mention what's important here. Why the rest of the proof is going to work out based on this inequality. So first, this quantity we have here compared to this quantity we have here. The k minus 1 squared is less than k squared. This is one part that's going to cause things to work out, and it's going to allow us to get, in the end, what we want, the ex of np equals big O of n. So the constant in front of this extremal function is less than the denominator of the n. So ex of np is less than or equal to this smaller constant times ex of n over a larger constant, comma p. And then the other part that's making it work is that this part right here, that part right there equals big O of n. So even if that was a much huger quantity in terms of k, like if it was like k to the million times n, that would still be big O of n because the k is a constant. So we have this inequality here, and we're close to what we want to get. What we want to prove is that at the end, EX of NP equals big O of N. And here is that inequality again. So this is not the problem. There's one last problem I'm going to give you, but it's not this bullet. It's going to be the next bullet. So given this inequality that we proved, here's the problem. And the problem is to prove the final result, that the extremal function of NP is big O of N. So it has a linear bound in terms of N. And we have this bound for every N divisible by K squared. So why can we get the linear bound for all N? So that's one thing you have to deal with. And I'll give you a hint for this result. So one way you can prove this is induction. That's one hint. The nice thing is there's actually multiple ways to go about proving this. So you can use induction. That will work fine. You could also think of it like a geometric series. So you can basically turn this into a geometric series. I'll let you think more about what that means, but the geometric series way is even faster. And if you do use that way, there was a result we talked about in one of the earlier 0 and matrix videos. So if M is less than or equal to N, P is a permutation matrix, then we can say EX of MP is less than or equal to EX of NP. So we proved that in an earlier video. That might be useful for this. It depends with how you prove it. So you prove it some ways, you might want to use that. If you prove it other ways, you might not need to use that. So see if you can finish off the proof. We've done almost everything. The last step of it is just a few lines, and you can do it either way you want. There's multiple choices. You can do induction. You can use a geometric series. There might even be some other way that I haven't seen yet. So I'll leave that to you to think about. And I think that is the end of this video. And that's the end of all the videos for this course. So thanks very much for watching, and see you later.